In this lesson today, we're looking at the process of partial fractions with the goal to be able to lead this into integration by partial fractions. Okay, so I've got a little bit of content to talk through here. Before we do that, I want to kind of outline the reason we're doing this. So we're looking at scenarios where we have some fraction. So let's say 2x plus 3 over x plus 1, x plus 2 with respect to x. The issue here is that the integration process, without splitting this into manageable forms, is going to be too complex. So what we're going to want to do is to find a process to split this into separate fractions so that the integrals will be simpler. So in this lesson today, we're not going to focus on the integration process. We're going to focus on the process of partial fractions. Now, if we can consider, let's say this scenario here, we have 1 on 2x plus 3 plus 5 on 3x take 1. So if we look at this scenario and we think of combining them together, so going back to year 10 and looking at our algebraic fractions, if we have to combine them together, we need to get a common denominator. So to get that common denominator, we multiply the first one by 3x take 1 on top and bottom. So now we have 3x take 1 over 2x plus 3, 3x take 1, plus 5 lots of 2x plus 3, as we multiply the second one by 2x plus 3 on top and bottom. And on the denominator, we'll have 3x take 1 and 2x plus 3. And so when that all comes together, we'll end up with 3x take 1 plus 10x plus 15 over 2x plus 3 and 3x take 1. Now we can continue this and we can simplify the numerator into 13x plus 14 over 2x plus 3 and 3x take 1. Our process with partial fractions will be to turn this simplified and combined version back into two separate fractions. When we're looking at this process, we'll have one of 4 distinct forms. So now we're going into these notes here. So it'll be one of 4 distinct forms. So it'll either be distinct linear factors. So we can see here that we have a linear factor and a linear factor. When it's in that form, we should be able to split it into 2 separate fractions where we have to determine what these parameters are equal to. If we have a repeated linear factor, so that's a linear factor raised to a power, then we'll end up breaking that into 2 separate terms. So one where we've got a linear factor, and again we've got a parameter that we'll have to calculate the value of, and the other one being in the repeated form. The third option is that we end up with a quadratic factor, and this is a quadratic that cannot be further factorized. So in that sense, we need to set it up with a linear over quadratic, and if there's any linear term, then we set it up in the same way as we showed earlier. Again, we'll have our parameters that we have to determine. And then our last step is if we have an improper fraction, and that is if the numerator is greater than the denominator. So in other words, we might have an x squared plus 2 over a 3x plus 1. This one is a quadratic, so it has a power of the leading term of 2, where this one has a power of the leading term of 1. If that power is greater on top, or if it's the same, so power is greater or equal, we'll first have to perform a polynomial division to simplify. So every scenario will end up being one or maybe a combination of each of these scenarios. So what I'm going to do is we'll look at the process first by determining which form to set it up into, and then we'll look at actually calculating the parameters so we can determine in full the individual fractions that each will break into. So the first example is we're going to break them up using the rules to set up the fractions that we're going to to work into. Now in this question, we are not calculating the values of the parameters. We're just setting them up in the first instance. So here we have two linear factors. With the linear factors, we want to break them up with a single parameter on top. So the two factors are x take 1 and x plus 2. So we'll separate them, and it needs to be a over x take 1 and b over x plus 3. Now when we continue these later on, we'll work out the values of a and b. A and b are parameters, and those parameters we can calculate the values. For this second one, we can see that we've got a linear, and this one is a repeated. So with a linear, it's nice and simple. It's just going to be a over x plus 1. But with the repeated term, we need to have two parts of it. So first of all is just b over the linear factor, and then c over the repeated factor. So we've got our linear, which broke into a over x plus 1, and then a repeated, which broke into b over x minus 1 and c over x minus 1 squared. In our next example, we have a linear factor, and we have a quadratic. And so this one, as long as this can't factorize, I'm going to assume that x squared plus x plus 1 cannot factorize into linear terms. Then it will break into the linear being a over x minus 2 as usual, and the quadratic term being bx plus c, so it's a linear term as a numerator, over our x squared plus x plus 1. Again, with each of these, our capital letters are the parameters that we'll be able to calculate, and we'll look at that process shortly. Now, this is our first one that we can recognize as improper. So the leading term on top is power of 5, and the leading term on the bottom is 2. The previous one, if we expanded this out, would have been a cubic. So therefore, 2 and 3, it's fine. This one ends up being a cubic on the denominator, so a linear and a cubic is fine, and a linear and a quadratic is fine. But here, we've got power of 5 on top and power of 2 on the bottom. So that means we have to start by performing a polynomial division. So we'll need to actually look at x to the power of 5 plus 2 divided by x squared take 1. So let's go through our process. Now, what I should have done here is we'll have our plus 1, but we'll have room for other things to go in there. So x to the power of 5 divided by x squared is x cubed. What we'll be subtracting is x to the power of 5 and x cubed. So I'm going to add in here a plus 0 x cubed. And so when we perform that subtraction, take away a negative, we get x cubed. We get our x cubed, and we still have our plus 1 up there. X cubed divided by x squared is x. And so now what we'll do is we'll subtract x times x squared take 1, which is x cubed, take x, and that means we'll throw in a plus 0x here so we can deal with that. And so we end up with x plus 1, if we bring down this 1, being our leftover, our remainder, because we can't divide x by x squared. So now we can write this as x to the power of 5 plus 2 over x squared take 1 is equivalent to our quotient plus the remainder. So here's our quotient, and here's our remainder. And so it will be the same as x cubed plus x plus 1 over x squared take 1. Now these are highly complex scenarios because now we have to consider our x plus 1 over x squared take 1, and we can think of that as x plus 1 over x plus 1 x take 1, and we can break that down into partial fractions looking at a over x plus 1 and b over x take 1. Okay, so this last one was quite difficult. The rest of them are pretty straightforward, and now we'll look at continuing each of these questions and calculating the value of the parameters. In most cases, we can use a process that's easy to calculate by substituting in known values, And I'll show you that now. So this first scenario we said was going to be a over x take 1 and b over x plus 3. Now the first thing we'll need to do is get a common denominator on both sides so we can get rid of the denominator. So this a is multiplied by x plus 3 and b is multiplied by x take 1, and it will all be over x take 1 x plus 3. So now we have 3x plus 5 on the same denominator. We can cancel the denominator and we end up with 3x plus 5 is equal to a lots of x plus 3 and b lots of x take 1. Now our goal is to calculate a and b. So the easiest way to do this, I know that if I sub in x equals 1, then this bracket will be equal to 0. So when I sub in x equals 1, I've got 3 plus 5. I've got a lots of 1 plus 3, which is 4. And I've got 0 lots of b. So I can get rid of that. So now I know that 8 is equal to 4a, and therefore a is equal to 2. The other thing that I need to sub in is x is equal to negative 3. So now I've got 3 lots of negative 3, which is negative 9 plus 5. And we've got 0 lots of a. And we've got negative 3 take 1, which is negative 4b. So we have negative 4 is equal to negative 4b, and therefore b is equal to 1. Which means that, if we go right back up the top, which means that our values of a and b are actually 1 and 2. So we've got 2 over x take 1 plus 1 over x plus 3. And that's our outcome. That's our process of partial fractions, allowing us to break this 3x plus 5 over x minus 1 x plus 3 into two separate fractions. Okay, when we look at the second example, we have this one as a over x plus 1, b over x take 1, and c over x take 1 squared. We want to get the same denominator as this side. So that means we need to multiply a by x take 1 squared. So to make it x minus 1 x take 1 squared, we need to multiply b by both x take 1 and x plus 1. And we need to multiply c by only x plus 1. And so we'll all be on x plus 1 and x take 1 squared. So now we can see that it's equivalent in the denominator to the original. And once we've got that, we can multiply by that denominator, and we end up with this 2x plus 10 is equivalent to a lots of x minus 1 squared plus b lots of x minus 1 x plus 1 plus c lots of x plus 1. So now we can go with our cover and check approach. So let's see, the first one that we can cancel out is we can let x equal 1. So if we do that, we've got 2 plus 10, and this a1 will be 0. We've got 0 squared, so 0 lots of a. We can cancel that out. We've got an x minus 1 here, so we'll have 0 lots of b, and c will be the only one. We'll end up with 2c. So 12 is equal to 2c, and therefore c is equal to 6. When we let x equal negative 1 is the other one that will work. So negative 1, because when we sub in negative 1, all the x plus 1s will be 0. So because the b and c will be 0, we just end up with negative 2 plus 10 will be equal to negative 2 squared, which is 4a. So 8 is equal to 4a, and then a is equal to 2. Now, we've got a and we've got c, but we don't know b. In order to find b, we want to let x be something else. Now, the easy one's always 0. So if we let x equal 0, we've got 0x plus 10. And we've got negative 1 squared, which is 1a. And we've got negative 1 multiplied by 1, which is negative 1b. And then we've got c, 0 plus 1. So we end up with 1c. Now, as we know that a is equal to 2, and c is equal to 6, we've got 10 is equal to 2 take b plus 6. So we've got 10 is equal to 8 take b. And when we rearrange that, we end up with b is equal to -4. So now that we've got all three, we can rewrite the original. We can say that 2x plus 10 over x plus 1 and x take 1 squared will be equivalent to a, which is 2 over x plus 1 take 4 over x take 1, and c, which is 6 over x take 1 squared. So back to our start, we've got a over x plus 1, b over x take 1, and c over x take 1 squared. So we'll move on to our last example. Now we're looking at a linear and a quadratic, so that's where it will be in the form a over x take 2 and bx plus c over x squared plus x plus 1. Now we want to get the common denominator again, so we've got our a lots of x squared plus x plus 1 and bx plus c lots of x take 2 will be equal to x squared plus 6x plus 5. I'm not going to bother writing in the denominator here because we've managed it so they will have the same denominator, so therefore these numerators will be equivalent. All right, we're going to take a similar approach, but it'll be a little bit different in terms of working out some remaining variables. So let's start with letting x equal 2. So when we let x equal 2, we've got 2 squared, which is 4, plus 6 times 2, which is 12, plus 5, is equal to a lots of 2 squared, which is 4, plus 2, plus 1, and because this bracket is 0, the whole second term is gone, so we're going to not even bother writing that in. So we've got 21 is equal to 7a, and therefore a is equal to 3. Now the next value that will help us is we let x equal 0. And this is so we can get rid of the b value. So when x equals 0, we've got 5 is equal to 1 lot of a, 0 lots of b, and we've got c lots of 0 take 2. So c lots of -2. Now because we know a is equal to 3, we can say this is 5 is equal to 3 take 2c. So 2 is equal to -2c, and c is therefore equal to -1. Now the only value we're left with trying to find is b. So if we let x equal 1, so it just has to be anything. So I'm choosing 1 because that's an easy value to sub in. We've got 1 squared plus 6 plus 5, so that gives us 12. We've got 1 plus 1 plus 1, so we've got 3a. And we've got b plus c, lots of 1 take 2, which is -1. And when we simplify that, we get 12 is equal to 3a minus b minus c. Now we know a is 3, so 3 times 3 is 9. We've got -b, and -1 is +1. So we end up here with 12 is equal to 10 take b, and when we isolate b, we get 10 take 12, which is -2. So now we've got a, we've got b, we've got c. If we go back up to the top, we've got a over x take 2. So the original function is equal to a over x take 2, which is 3 over x take 2, and bx plus c, so -2x take c over x squared plus x plus 1. And there we have it, simplified down into partial fractions. Okay, so that concludes this lesson. There is a lot. The process of using partial fractions is a complex one, and one that takes a bit of practice. Even looking at breaking into these individual fractions for a start will be difficult. And then after that, calculating those parameters for a start will be difficult. And once you get to a point where you're fluent at it, it should be a relatively fast but still complex process. So make sure we practice, keep referring back to these breakdowns, and good luck with your practice.